down into individual amino acids all the time. Caroline. They're in the polar environment that don't hydrolyze it all the time, but we have to remember in what environment are proteins? Where do we find proteins? Enzymes, receptors, we find them in the cell. And what is the cell? Mostly water. Right? Okay, so but let's say, all right, so the interior of the protein is non-polar, so those are protected. Those are good. But what about the outside? Well, they're still exposed to the water, so those will be broken down, and that'll expose the ones on the inside, which will be broken down, expose the ones on the further inside. So eventually it should all be broken down. Why don't they? A lot of hydrolysis reactions require enzymes. Okay, we're getting there. Why do they require enzymes? They have a high activation energy, right? So if we have, protein in solution for, 100 years, yeah, they'll get broken down, but not on a time scale that matters to us. So what this actually looks like is something like this. Right? Yeah, of course the delta G is negative, right? But we have such a high amount of energy that we have to find to achieve the transition state, right? That it's going to happen very slowly. And this is why we need enzymes to break peptide bonds. They stabilize this transition state. They provide a lot of energy through their weak interactions that make this easier to achieve, coming up like that, right? All right, where are we? Okay, last question here. An enzyme catalyzed reaction A yields B. We want to make design a drug that inhibits this enzyme catalyzed reaction. Okay? A, what should the structure of the drug resemble? And why would this be particularly difficult to make? Okay, so let's start with the first one. What should our drug look like? Notice I haven't given you the structure of A or B. Isabella. All right? Would have to resemble A? Why are you saying?
Possibly in order to occupy the active site.
Okay. Right, so it's got to occupy the active site. But is it going to occupy the active site as well as A?
Probably not.
Probably not. Okay, so what else could fit into the active site? The transition state, right? So the transition state. So if we want to design a drug, right, we want it to bind better to the enzyme than the substrate. Otherwise, the substrate will be able to outcompete the drug and it will be not very effective. So we want something that looks a lot more like the transition state than it does the substrate to maximize those interactions, right? To outcompete for the active state. Now, why would this be particularly difficult to make? See someone who hasn't talked today.
It's a high energy intermediate that's unstable.
The transition state is sure, right? But we're not making the transition state. We can't make the transition state because it's so high energy. It really doesn't exist for any appreciable amount of time. As soon as it's made, it collapses into either A or B. So you are correct. It is too high energy to synthesize the transition state, but we're not making the transition state. We're making something that looks like a transition state.
We don't know for a fact what transition state will be, we hypothesize what it is.
Sure, I guess. You can't isolate the transition state, but we're pretty good at predicting it, right? But even though we're not making the transition state because it's impossible, right? Your answer is like halfway there. We're making something that looks like it, so it also will be high in energy. Just not so high in energy that it immediately collapses into A or B. So these transition state analogs, which are what drug design is usually trying to deal with, right? They're difficult to make inherently because they resemble these high energy compounds, the transition state. They can't be the transition state, but they have to look enough like it. And by virtue of them looking like it, they'll be intrinsically high in energy, which makes them less stable, which of course makes them difficult to synthesize. Alright, so we've talked about these already today. So we'll end there, okay?